All right, so let's get started. So our next speaker, Nikhil, is gonna talk about the reasoning about anonymous object interactions using plan failure as metacognitive trigger. All right, let's welcome.
All right, thank you. Everybody hear me okay? Good, okay. Yeah, so my name is Nikhil Krishnaswamy. I'm from Colorado State University. The title of my talk is Reasoning about Anomalous Object Interaction Using Plan Failure as a Metacognitive Trigger. Put on the spot to come up with a talk title, I put the word plan in a little bit rashly. This isn't necessarily about planning, but mostly about what happens when you follow a stupid plan and then have to reason about the result. So, okay, let me see if this works. Am I pressing the right button? Do I press the arrow? I can always just drive it from the... Okay, yeah, okay, all right. A non-trivial amount of my lab's research comes from me watching my children play with objects, specifically my daughter play with blocks. So here she is. From the prior literature in developmental psychology, there comes this notion that as humans are mapping concept representations to things like nouns, they're also at the same time learning to individuate them from the perceptual flow. And this is done not just based on visual features, but also based on the experience in interacting with those things. So in my work, we usually take this embodied simulation approach to things like language grounding. This has led us to a couple of different notions of what you might call embodiment. So the first one is kind of what you might think of as typical notions of extents and articulators. That is, if I have legs, I can do certain things. If I have arms, I can do certain things. But then there's also notions of what we're calling sensory embodiment. That is, the different types of input signals that we consume as we are going about our interaction with the world is also going to condition how we represent the problem space. So in a nutshell, physical embodiment conditions action, sensory embodiment conditions perception, and other types of downstream reasoning. The way we explore this is usually by using a virtual environment to create experiences where we have an agent interacting with various items. And in particular, by virtue of me getting research ideas from my kids, doing a lot of stuff with object-based reasoning. So when you are interacting with an object, the motion of that object will leave a trajectory in space. And broadly, this is going to be based on the geometric properties of the objects and also their affordances. So here, for example, is a cone being stacked on top of a cube, and you can see that when the cone is placed with this flat side down, it tends to stay still on top of the cube. And often we see the cone, when it's on its side, is on the floor, having rolled off the cube. This is basically just because of what that object affords in different configurations. So we can see here there's some GIFs of different objects being stacked upon this cube. This is sort of one of our go-to ways of collecting data. And you can see that, for example, the cube in the top right typically stays balanced, where other objects like the sphere are almost impossible to stack and keeps rolling off. And then there are other objects like the pyramid that is all flat sides and usually stays stacked, much like the cube. And then there are some objects here, cone and cylinder, that have this kind of dual aspect. They're flat in certain orientations, round in other orientations. And so the orientation is an important factor in what happens to that object. So not only must you place it correctly, it also has to be oriented correctly if your goal is to stack the object. We do all this in a platform that I've been developing for a while called VoxWorld. It's basically a underlying platform for creating different types of interactive agents. In the data that we collected in this type of object stacking task, which is what I'm going to use as a jumping off point for the remaining research, the agent is presented with a cube and one other instance of another object. We'll call this the theme object. In the object set that we have, which includes these things here, and also cubes of different sizes and rectangular prisms and the like, we see that there are pairs of objects that show minimal distinctions, such as flat and round sides, or length along an axis, and other factors like this, where if you pair objects off, you can find these types of minimal pairing distinctions between them. The agent will sample from the environment by stochastically placing the theme object on top of the destination, the cube, and if the resulting configuration is stable, the theme will stay still. If not, it will fall off. And this is something that I've observed my daughter learning to do, as she's growing up. Of course, there's a problem in that a virtual environment can be hyper-realistic in that even with a sphere, for example, if I move it to exactly the right location, it will probably still stay still. And this doesn't really reflect some of the stochasticity that occurs in the actual act of stacking. There's a little foible there with the images. So what we do is we simulate some more realistic physics in the environment by creating a jitter that's derived from representation of the object semantics. We have a representation language called VoxML. That's something I've been working on starting in my graduate studies. What we do, among other things, is represent things like factors about the object symmetry and rotation and its different components. So for example, here's a cylinder that it has rotational symmetry around its y-axis. So y-axis by convention, our environment points up. The cylinder is symmetric around that. This will, when I place the object, then simulate a type of perturbation that is perpendicular to that axis. What that means is that when the cylinder is placed upright, it might move a little bit, but it's unlikely to, say, tip over and roll. But if the cylinder is placed horizontally on its round edge, that perturbation is going to cause it almost immediately to roll off. So these distinctions in behavior correspond to distinctions in the habitats, that is the conditioning environment that allows certain behaviors or affordances to take place, in this case as they pertain to the, quote, stackability of the object. For our data, we gathered 10,000 samples of each object instance. Object types are enumerated there. And then we basically captured a bunch of numerical information describing the trajectory of the object in space when it is placed. So the action that was taken, how the object is oriented before and after the object, or before and after the action, relations that exist between different objects in the scene, et cetera, et cetera. If we look at some of the things we can do with this type of data, we can compare the ability to simply do object classification using this trajectory data compared to images. So when we see this here, I'm not going to delve into the details that are presented on the slide, but we can see that when I am using the image data versus the trajectory data, at a low data setting, the trajectory data allows us to achieve a much higher classification accuracy of the object type. Naturally, the images do catch up eventually, but the number of samples per each object is required to be quite a bit larger. And so in this low data environment, the object trajectories that embody the problem space seem to be a lot more useful. So what we bring to this work is a distinction in the embodiment of the agent within the environment and how that allows the agent to make certain types of inferences about things that it knows or, in some cases, doesn't know. Further, we'll examine some mistakes made by the visual classifier, and we can see that, as expected, a lot of these are related to things like visual artifacts, such as perspective and foreshadowing and occlusion. And so when we add the data gathered through the trajectory information, this helps even in cases like these, because what happens is that even if I can't see an object, if I know something about how it was moving before it moved out of view, I can still perform reasoning about it. So we can see some examples here where objects are occluded and it's misclassifying what's intended to be a cylinder as a cube because a cube is in front of it, or a capsule as a sphere because it's pointed right toward the camera and it can't tell where the depth distinction is intended to be. So we take this further just by demonstrating that this type of information seems to be useful, but how can we use this type of information input sensing for certain types of metacognitive tasks? Now, metacognition, of course, is the topic of this workshop. It can mean a number of different things, and we've heard a lot of perspectives on that in this workshop, many of which you will see echoes of in this talk. But broadly, what I'm speaking of in terms of metacognition is an ability to tell when a model is inadequate to a situation. So that is, can a model itself figure out that it does not know, or that it's something that it doesn't know something? Can a model know what it doesn't know? We are, of course, inspired by humans. Humans are very known for seeking out informative experiences and learning through just a few samples. Prior literature has shown that artificial neural networks require approximately 5 to 8 layers of artificial neurons, and this particular paper did not specify how many neurons in that layer to approximate the computational power of one cortical neuron. Additionally, artificial neural networks also don't easily expand to accommodate new concepts given a few unseen samples. This is a well-known problem that many of us in this room are attempting to tackle. So we're investigating this through the angle of embodiment and interaction. And so these, quote, metacognitive processes need the system to be able to identify things that it already knows and things that it doesn't know and be able to tell the difference between them. So first, we conduct just a basic similarity analysis of the objects. So using the same data, we simply attempt to classify them, and now you can see some multidimensional scaling on the final hidden layer. You can see some level of misclassifications in the orange box here, and so for example, we can see cylinders that are confused with things like cones or capsules, things that share certain properties regarding symmetry and motion. but are different in perhaps the specific geometry of the object. We can also see the confusion matrix there on the right. So what we then do is we're trying to figure out what features are most important. So that is, at a high level, what concepts has the network modeled to make these distinctions. So what we do is we take an iterative approach. We begin by training a standard feed-forward architecture on just a subset of the objects, in this case, cube, sphere, and egg. One kind of canonical flat-sided object and a canonical round-sided object, and one that is round but also has one of these axial distinctions. So after we train this, we then add one object class at a time to the vocabulary, and we freeze the first two hidden layers of the source model and add another layer to conduct further learning. So the source model is going to be trained on k-1 objects and then fine-tuned to a target model with k object. And what we find is that as you add more objects to the vocabulary, the number of fine-tuning samples required to achieve a target accuracy goes down. And so this seems like this type of dynamically growing model is modeling some underlying distinction between these object types. So we can see here some other examples of the confusion matrices using this type of transfer learning, so starting with the base and as we add different objects. This is able to maintain a high classification accuracy by incrementally introducing objects, and we see that the number of samples per object goes down for the fine-tuning. Additionally, when we get to the final model that has accommodated all of the objects, we see that we get a final accuracy of 90%. So then what we did is we trained the same model architecture that resulted in all of the data and found that the best accuracy that we could get was about 10% less. So this way of incrementally adding concepts appears to be able to model some important distinctions. So what are those? We know that objects are not just instances of multiple classes. We also find that there are these properties and contrasts that adhere across multiple object types, as I discussed earlier. So obviously we have both round objects and flat objects, then we have these cases of, say, cylinder and cone that have different, both of those aspects. And the data contains the rotation of the object, which correlates to the round or flat edge upon which the object rests. So then what we did is we resplit the data according to basically flat side down, round side down. And then we applied the same fine-tuning procedure to the model that was trained over all the objects to see if it can infer these relevant contrasts independent of the object type, and we're actually able to do that with 100% accuracy. This shouldn't be all that surprising given the data that has already been modeled within the network. So then we wanted to look at how we can use this to detect if something is unknown to the model. So we've got objects that have, say, flat sides, round edges, something of both. If I know of only, say, all flat, all round objects, am I able to detect something that is neither one nor the other? So what we do here is we take a slight variant on the data collection procedure. We train a TD3 algorithm to stack blocks. So here, these are just the training reward plots. So we have two policies that I'll focus on called the accurate policy and the imprecise policy, just one that was better optimized toward the end than the other. We also have a thing here for the perturbed policy. This was just manually moving the solution in the action space to make sure that we weren't just like overfitting to a particular location, and it's still able to train, so that seems to be sound. So having trained this network to stack blocks, we then use that trained policy and attempt to stack a variety of objects. So that is, all I know how to do is stack blocks. When given an object, I will then attempt to stack it as if it were a block, because that is all I know how to do. Then we store the same information with the addition of rewards, and we can see just in the reward plots some substantial distinctions between these sets of objects. So we focused on cube, sphere, cylinder, and capsule, and then also a cube of smaller size where the only distinction is one of scale. And so basically what it means is when the reward is high, stacked well. When the reward is low, did not stack well. Cube, easy to stack. Cylinder, also fairly easy to stack as long as the orientation is correct. Sphere, almost impossible to stack. Again, fairly intuitive given what we know about the object. So we can see that there are distinctions here, and if I have an object classifier trained on, say, cube and sphere, that should be an easy distinction to make based on the information that we gathered. So this data, what we did is we have 10 episodes where during testing. So this is now time sensitive in that if I stacked the first time, the episode ends. And so then what I can do is to make sure that I have a fixed size input, I'll just pad that out to the requisite length. So let's say samples of 10 episodes that are concatenated should maintain a steady state, whereas things that stack, or the things that fail to stack repeatedly are going to have different feature vectors at every time step. Concatenate those, it should show that. So we then train a 1D CNN classifier on a subset of objects. So for example, we would train only on cubes and spheres. And then what we want to be able to do is, if I see a cylinder, can I identify that it is not something that I already trained on, not a cube and not a sphere? The way we do this is we retrieve the embeddings for the objects and just compare them to the similarities of verified known samples. There's a particular formula that we use to account for things like differences in weight initialization that are going to affect the embedding space, but this basically becomes an outlier detection problem. So if a set of vectors falls substantially outside of the subspace or region defined by samples of a known object, they likely represent a new type of object. And so then what we do here is just try to detect which objects are new, given that our model has been trained on, say, a cube and sphere, or a cube, sphere, and cylinder, or a cube, sphere, and capsule, or all. If the model is trained on all, effectively this should always tell me that nothing is new, in addition to being able to classify cubes of a different size as also instances of cubes. And we see that there are two things here that I'm showing. One is there's both the accurate policy and the imprecise policy. And then on the left, I'm showing the ability to classify objects as novel or not, given that jitter that I referred to earlier that implicitly encodes information about the object affordances or not. So here we're showing it without the jitter, here we're showing it with the jitter, and so basically this additional signal of how the object is situated within the environment causes, on average, about a 25% boost in performance. Interestingly also, the order in which you're training the model matters, in that if I have cube and sphere and capsule, we see lower performance in that it's much harder to identify that cylinder is new, largely because the capsule has a great diversity in behavior, and so that's taking up more, quote, space in the latent space. And so it's harder to optimize a decision boundary between, say, what is a capsule and what is a sphere. So we see that adding that information that is implicitly encoding the habitats and affordances results in a fairly impressive performance boost. We can also look at the confusion matrices and see the types of misclassifications that we are encountering. And in particular, we'll notice that there are lots of confusions between, say, sphere and capsule and cube and cylinder. And so when you think about it, if I have a cylinder that is stacked vertically with its flat side down, it's behaving a whole lot like a cube, and I'm not getting that additional signal about the object symmetry where that's located relative to the rest of the environment. So without that implicit good encoding of habitats, we see that the cubes are confused with cylinders and the spheres are confused with capsules. So this type of embodied information within the environment seems to be pretty critical to be able to do this type of novelty detection task. So the next thing we do is I talked about how we seem to have inferred these different kind of flat versus round classes in our data. So tried to bear this out in another way by doing a similarity learning of the object properties, again, over a subset of objects. So this is just a deep pair-based learning approach using a multi-similarity loss given by the above. What we do is we train only on a subset of the objects, that is cube, sphere, egg, capsule, small cube, rectangular, prism, and pyramid. These are all objects that are only flat or only round. Then we have our two objects, cylinder and cone, that are both. So in the train and the test set, we have samples of flat-side objects and round-side objects. The flat-side objects were ones that were stacked successfully, and the round objects were the ones that did not stack. And then the test set will include the 7 seen classes above and also the 4 unseen classes, that is cone and cylinder, split according to their behavior. So with this approach, we're able to successfully classify the geometric features into different object types. This reproduces the previous result. And we also see that by just using a KNN over the embeddings, those 4 classes that occur in the bottom right are also classifiable. We see that there is a non-trivial number of confusions, but where those confusions arise in the unseen data are between different flat and different round objects, never between these classes. So this confirms that the model appears to learn this contrast between flatness and roundness, even though it was never explicitly modeled in the training data. We also look at we can take a PCA plot of the resultant space, and we can see that there are these 2 distinct clusters where the items are color-coded according to their both their broad class outlined in blue or orange and the individual classes of the object. Okay, so what does this mean for the plan in the title, the planned failure in particular? So most of my research actually gets started in language modeling. This is how I kind of got into doing AI research in the first place. So with the advent of things like ChatGPT, this gives me both a new tool to play with and then also a way to conduct examination of these types of reasoning problems that I have been previously exploring. So what I did at one point is I put the following prompt into ChatGPT. I need to get to the top of a platform that is 2 meters high. The highest I can jump is 1 meter. I have 2 cubes that are both 1 meter long on all sides, a sphere that is 1 meter in diameter, and a cylinder whose major axis is 1 meter long. How can I get to the top of the platform? It gave me the following. Then what we did is we took this instruction and reproduced it in the Unity environment, and this is what resulted. And I don't know about you, but my 2-year-old who likes to throw herself off things might think this is acceptable, but any reasonable person with a sense of self-preservation is going to look at that and say, I'm not touching it. So it told me that I should do this, and it will successfully reach the top of the 2-meter-high platform. But if I look at this, not only would it be not possible to stack these objects in this way, I also would not be able to climb them as I'm assembling it. So I'll let you think about, given the object description that I have, how you might solve this problem, and I'll show how we eventually train a model to do that. But this is sort of how we're starting. So what happens if I have a stupid plan and try to follow it? Well, that's the result. So this, of course, raises a question. This result seems to be intuitive for a human, at least one who has accumulated a level of life experience allowing them to preserve their own well-being. But we also know that LLMs do display a level of world knowledge about individual objects, but doesn't seem to be able to put that together in a way to satisfy the thing that I asked of it. So in other words, I want to go here, and I have these things. So you can think about how you would put those things together in order to do so. Okay, something went wrong here with the exports, but if I'm following ChatGPT's plan, it would ask me to place a block, stand on the block, put a sphere on the block, stand on the sphere, put a cylinder on the sphere, and stand on the cylinder. And you can see that eventually you're going to fall flat somewhere. There was supposed to be an X that occurred after it put sphere on the block. If I attempt to execute, right, we kind of fail at this point. And so I'm trying to figure out, given that I have failed at this point, what should I have done instead? And what can I do with the objects that I have available that will allow me to proceed along some sort of plan that would eventually lead me to the goal? So if you return to this problem with the cube stacking, we can look at the reward plots for the different objects that I've got available. And we might be able to make some inference based on that about which object type might be most suitable for this task. And we can see that if I know what I can do with cubes, let's say I would normally do this task with 3 cubes, but I only have 2, I've got to pick a substitute. So sphere appears to be the most dissimilar to cubes. That's probably not a good candidate. Cylinder looks like it might be. But as we've observed, there are certain conditions that have to be applied in order for this to actually be the case. So here's cube, and here's cylinder. These seem to be the two that would be most suitable for this task. So we know the cubes are not the only things that can stack. So now I'm trying to determine which of these could substitute for a cube and also how. So our similarity classifier has these non-overlapping cube-like and sphere-like cylinders. So if we split them according to their label and the orientation, we can see that I've got a cluster of what's denoted as cone F and cone R. So this is cone R, kind of takes up this space. This is cone F, kind of takes up this space. They overlap with other objects in those flat and round categories. So the cylinder is unseen by the model. So basically what I'm looking for is an analogy. Cylinder plus some variable is to cube, as cylinder plus some other variable is to sphere. I'm trying to tease out the nature of those variables. So the approach that we use is basically we have these 40-dimensional raw features. We feed them into the similarity model. This is going to give us a representation space that lays out something like this. And then we'll see that some subset is going to end up in the flat cluster, some subset is going to end up in the round cluster. We then just have a set of labels about like which object is this most similar to. And then what I can do is I can take the features and the output labels and just index them and say, well, when I was interacting with this object like this, it displayed properties similar to this other one, and when I was interacting with it in another way, it displayed properties similar to a different object. And this gives us feature vectors that we can tease out from those raw features to say, what should I do with object X in order to make it behave like Y? And so we can see here, here's some examples. So you can see here one where in this new environment, we have our player, who is a cube, navigating around the world and sampling different objects. So what it does first is it will just take the object and place it, in this case, on top of itself to simulate the original environment in which the data was collected, and we can observe how those objects behave. And then once it's done, it'll place them in the target location. Currently, that's just done by teleporting the object to there. We didn't implement the full path plan to carry it to that point. But you can see here's one such case where first it placed the cube here, then it experimented with the cylinder, determined how it should place it, and then moved it to that location, and then did the same thing again with the cube. We'll see another instance here where it explores the objects in a slightly different order and actually starts with the cylinder, I believe, to see what should I do with this object in order to place it at the appropriate orientation. You can see that result here. So there's the cylinder, there's the cube, and then now it's experimenting with the other object, and then it finally places it here and creates our staircase that would then allow me to jump up to retrieve that green object. A couple of things here that I don't really have on the slides is that this created a pretty interesting like sim-to-sim problem in that the original data was gathered in a different environment. And this was kind of on me because I neglected to tell the student who made the new environment that I wanted the objects to be of a certain size, and so we just went ahead and made them at a radically different scale. And so then having to transfer the object representations from the original similarity model to something that could be have inference performed over it here necessitated unifying two different representation spaces. What we can do there is we can take samples from one representation space and then samples from another representation space that we know or are relatively sure represent the same information, pair them, and perform a ridge regression between those two spaces to get a robust transfer from one type of simulation to another. So why doesn't a large language model know that this is incorrect? And how can we predict when it will generate such outputs? So that is, I want it to not do this. I want it to do something like this instead. I need to know when this is going to result in a failure to my anticipated plan such that I can perform in-situation reasoning about how I might be able to solve that. So we have a couple of options for how we are going to further explore this problem. I'll talk about option B first because that's effectively what you just saw in the demo GIF. That is, I have my simulation environment, and then what I can do is I can have my environment rewind the situation and then try different actions to create counterfactual outcomes. This allows us to realize things in terms of, say, Judea-Pearl's do calculus, where given that I took some action A, what is the probability of outcome B? Then explicitly simulate some situations where I did not take action A, and then assess the distribution of probabilities of outcomes to see whether A is a determining factor in the success of B. This is fairly compute intensive because you have to run the simulation backward and forward repeatedly. So we have another avenue we're exploring, which is looking in the latent space. You have, obviously, in the policy space, right, one layer before that, you've got kind of an embedding of the action. So you take those embeddings and then map them into the object embedding space. You can measure the distance of the transformed action embedding to the affordance embedding. And then you can consult, say, a knowledge graph or raw features, tease out those relevant factors, and then project those resultant states back into the policy embedding space, sum them to the actions, and then transform them back into the affordance embedding space to see if the new action got you any closer to the result that you desired. That's as far less compute intensive, but of course, given the amount of transformations that are ongoing, there's a substantial amount of noise that could be introduced. So we hypothesize that some combination of the simulated exploration and reasoning within the latent space can allow us to do this in a more robust fashion. There's a critical problem in that LLMs just simply won't admit to not knowing something in most cases. And so what we also want to do is we want to be able to take the information that we learn from doing this type of in-situation embodied reasoning and then allow the LLM to create reasons or rationales for why it could or could not do something. So here's kind of a toy example. So if I have this subset of my plan here where I put the sphere on the block and it fails to let me stand on the sphere, in my knowledge graph I may have some representation of, okay, the sphere is round or the sphere rolls. If I can take this and then concatenate it with a representation that comes out of my embodied representation space, project that into an LLM space and conduct more fine-tuning, my goal would be to create outcomes like I could not stand on the sphere because it is round and roll it off the block I placed it on. And this would, in principle, allow us to better reason about why, say, the initial outcome that I got out of ChatGPT was not a good one. So in conclusion, and I'm not entirely sure how much time I actually took up, but it seems like that's not an issue. So despite their power, these modern generation of LLMs seem to struggle with certain classes of problems. I focused on physical reasoning problems, but also metacognition appears to be one of these things that LLMs are not particularly good at. Most of my research has focused on these physically grounded problems relevant to things like HRI. And one reason that I hypothesize this is largely the case is that text alone misses a lot of the unseen information that a grounded reasoner would both have and need. Someone that I might derisively call an LLM triumphalist might say that with 1 trillion more tokens we'll solve this. And while I acknowledge that we will continue certainly to be able to leverage the power of data and computation, what we get out of the latest generation of AI systems is useful but flawed information. Generally, I'm of the opinion that the burden of proof is not on LLM skeptics that LLMs cannot do a thing, but rather on LLM believers that they can. Reasonable people can disagree, of course, but this happens to be my position. A foundation of metacognition is that a model must be able to identify what it doesn't know so that it can perform reasoning about how to get around those gaps in its knowledge. The approach we presented here raises questions on the fidelity of simulators and geometric techniques that are used to make these inferences, and also shows that embodied interaction can readily expose these gaps in the quote-unquote knowledge of a model. And thanks to my student collaborators and folks that have funded versions of this research.
Great.